Hello, in this video I'm going to provide you with a general overview of electricity. The content and language objectives. First of all, I can distinguish between series and parallel circuits. Second, I can write my own analogy about voltage, current, resistance, and power. And so in this video, it's not going to cover math concepts specifically, but series, parallel circuits, circuit symbols, different equations that are used and units that are used with electricity, and then a little bit of information on electrostatics. So first, different types of circuits. There are two main types of circuits, and those are series and parallel. In series circuits, what you have are all components that are arranged in a series. I think of like a book series where you read the first book and then the second book and then the third book. What you notice here is that in this circuit, and we'll talk about circuit symbols in just a moment, all the different components are on one big loop, on one big path. On the right-hand side, on the other hand, that is a parallel circuit. And what you can see is there are literally parallel lines where different components are located on in this circuit. So in the example to the right here, there's one pathway that the first rectangle, that component is on. There's a second pathway that electricity can flow for the second, third pathway furthest to the right. In terms of circuits, when you look at circuits, there are a bunch of different symbols. We'll use shorthand symbols to represent components such as resistors, switches, light bulbs, and batteries. And so what these different components are and kind of what they mean in the pictures to the right. What a resistor is anything that slows the flow of electricity. A switch is just like a light switch that you can turn on or off that would allow electricity to flow through some area or not. A light bulb can be drawn as a sort of a hump in a wire. All of the straight lines in these examples are supposed to represent just wires connecting different components. It can have a little hump in the wire with a circle around it, or it can be drawn with a circle and an X. And then a battery or a cell is drawn right here. And what you can see is they are perpendicular to the wire. One's a little bit longer than the other, and these two line segments are parallel to one another. So in the examples to the right, just kind of tying the last two concepts together, you have two different circuit diagrams. Letter A up here, these two light bulbs that you can see right here, they are in parallel because they're on different pathways. You can see in this example, there are three light bulbs in total. There's one resistor, there's one open switch, and so electricity would not be flowing through this pathway right here, and there's one battery. On the bottom, example B, what you can see is that there are three different resistors that are shown here. There are three different light bulbs, and there's only one pathway for electricity to flow through. So these components, they are all in series. Examples of circuits in the household, you would have all sorts of things around your house that involve circuits. And just a household fan that's sort of being deconstructed, here, is one example. Different components and where you'd find them. So a switch would be used to turn an object on or off. And so if you turn on or off your fan, what you're doing is opening or closing that circuit so electricity can pass through it. Resistor, if you are changing the speed setting on your fan, what you're doing is changing the resistance, changing how much electricity can flow through a given area. Light bulb, would be lighting up these different components. So if you have little LEDs here, that is a light bulb that you'd find in these fans. In terms of voltage, current, resistance, those are some terms that you'll see, some different units. We'll see amps, volts, and ohms. These different electricity concepts, the issue with these is you probably don't have a ton of background experience outside of maybe use with technology, use with like a cell phone charger or voltage that you'd see on a battery. But the different components, what they are, current is the flow of electricity. And so you can see this little amp here. The measure of current is amps. Capital A, or sometimes you'll see an abbreviation of an I, represents current. And so current is like the flow through this pipe here, if you're using the analogy of water flowing through a pipe. Voltage is like electric potential or electric push. And so a 9-volt battery would have more push than a AA battery that's 1.5 volts. Measured in volts, capital V is used to represent that. And then resistance is shown by the cowboy ohm here that's slowing the flow of electricity through this pipe. So an omega is used, the term ohm, the symbol R is used for resistance. And so we will cover separately voltage, current, resistance, some examples with math. But if you look at the cookies that are shown here, or triangles, or sometimes how these are shown, voltage is equal to current times resistance. If you cover the V in this VIR cookie, you have I next to R, so I times R. Resistance is voltage divided by current. Current is voltage divided by resistance. And so we'll talk about those later. Just an analogy, or a couple analogies for voltage, current, resistance. One is shown here. It's like a water hose, where voltage would be like the pressure in the water hose. Current would be the flow of water out of the hose. So if you have a larger hose, you can have more current. And then resistance is anything that's going to slow the flow. So if you were to stand on the hose, that would slow the flow of electricity or water. Also, if you had a whole bunch of sand that was stuck in your hose, that would slow the flow of water here. Just another analogy, and I like this analogy a little bit more for voltage, current, resistance. If you have resistance, it's something that's slowing the flow of traffic. And so you can see here, if there's a bottleneck in traffic, that would be high resistance. If you have three different things slowing down traffic on the same route, that would slow things considerably. But if you have a larger highway, that would have a higher current. And even if you have three things slowing down the traffic on this greater highway, you're going to still have some better flow of traffic. Electric charge. Electric charge is another concept we'll talk about. And electric charge can be shown as these little electrons that are flowing along this circuit. So this circuit is just from a FET activity that we'll take a look at later. But what you can see is that if you had an open circuit, there's not going to be any electrons that are moving through this electric circuit. And so what would the flow of electricity be, the current? It would be zero. You have zero charges moving per second. And so charge divided by time, the number of electrons moving per second, if you want to think of it that way, is what current is. If you have in this picture here a resistor with a resistance of 10 ohms, the flow of electricity is going to be pretty low. You have few electrons moving through this circuit section per second, while at the light bulb here, if you have resistance of only 5 ohms, there's less slowing the flow of electrons, and so you'd have a higher rate of charge in coulombs per second. Electric power is the final concept with final, I guess, unit that we're going to talk about. And this is one you might be a little more familiar with chargers. So if you have a fast charger for your phone, you might charge at like 20 or 45 watts. But watts are the units for power. Watts are kilowatts. It's like the flow rate of water. And so you can see in the picture to the left-hand side, if you have a battery and a light bulb and there's 5 watts of power, you can see that the light bulb's not very bright. The example on the right, if you have 10 watts of power, it's higher. And so light bulbs are also rated for wattage. And so a 60 watts incandescent bulb, like traditional light bulb, would be standard, just to give you an example of that. And so what power is current times voltage. It's the flow of electricity times that pressure, if you're talking the analogy with water. And so again, we'll cover this concept, mathematic concept later. The last topic that we will talk about today is electrostatics. And so everything we've been talking about is flowing electricity so far, but you also can have an electric charge that does not move. And so that's what static electricity is. Again, we'll take a look at a FET simulation later, but if you look at the balloons here, if you rub a balloon against your head or you rub your balloon against a sweatshirt, what can happen is you notice that maybe your hair sticks to this balloon. The balloon sticks to your shirt. And the reason that is you have protons, neutrons, and electrons. Electrons which can move pretty readily. And so you can end up with partially positive and negatively charged particles. And so objects will repel each other or attract each other because of electrostatics. The closer two objects are, the greater that attraction or repulsion. Another demonstration we'll do later, you can deflect water with a comb if you build up a static charge. And so we'll take a look at that later. The final thing we will do with electricity is we will talk about a Van de Graaff generator that does sort of the same thing, building up a static charge. And so if you've seen one of these before, we'll get a demo of that in class. That's the end of this video introducing electricity concepts. If you have any questions, please always feel free to stop by during homework help or period 1A. Thank you very much and have a great day.